In this lesson, we will compare consistent systems with inconsistent systems and explain what to do when you encounter an inconsistent system. Up to now, we've studied some systems of equations and been able to solve them. Every system that we've worked with up to now has been a consistent system, that is, a system which has one or more solutions. Some systems we will find don't have any solutions. Those are called inconsistent systems. Those are systems which have no solutions. We found that to solve a system of equations, we need to find all of the points that satisfy each and every one of those equations. If by chance the two systems or the two equations don't have any points in common, then we get what we call an inconsistent system. Let's take a look at an example to see what we mean by this. In this example, we want to solve the system x equals 18 plus 3y and 2x minus 6y equals 12. I can solve this system using any of the methods that I've already learned so far. I could solve it by graphing, but when I'm looking, I'm seeing that one of the equations is already solved for x. That will make substitution very easy because I already know what x equals. So all I have to do is substitute into the other equation. So I'm going to start with that other equation. So I'll write 2x minus 6y equals 12. And what I'm going to do here is substitute in this value for x into this equation. So I'm going to substitute into x here. So I'm going to rewrite this equation, only instead of writing an x, I'm going to substitute in 18 plus 3y for x. And then I'm going to just continue writing the rest of the equation. And now I can simplify the left-hand expression here. I can change subtraction to addition by adding the opposite. And I can also distribute this 2. This is going to give me 2 times 18, which is 36, plus 2 times 3y, which is 6y. Everything else comes straight down, so I need to have plus negative 6y equals 12. Now, I can continue simplifying. I can combine these two like terms. 6y plus negative 6y is 0y. So this is 36 plus 0y equals 12. Well, 0y is just 0, and 36 plus 0 is 36. Now my equation reads 36 equals 12. A quick glance at this will tell you that all of my variables have gone away. There are no more variables in this equation, and I'm left with an equation that says 36 equals 12, an equation that's clearly not true. Alright, so this equation is not a true equation. This is an indication that this is an inconsistent system. This is a system which will have no solutions. Now, this is a little bit hard to understand by looking at this from only the substitution perspective. So what I'd like to do is I'd like to see what happens when we solve by graphing. Because remember, solutions to a system of equations are the points where both equations are satisfied. So what should happen when we try to graph them? Where will those points in common be, or will there be any? So let's take a look at this. I'm going to graph the first equation in green, and in order to graph it effectively, I should put it in slope-intercept form. And to put an equation in slope-intercept form, I need to solve the equation for y. So this is going to be x equals 18 plus 3y, and now I'm going to use the steps in solving an equation to get y by itself. I'm going to get rid of all terms without my variable in it by adding the opposite to both expressions. This is going to be x plus negative 18 equals 3y. Now I need to multiply both expressions by the reciprocal of the coefficient, which is 1/3. In this left-hand expression I have terms, so I just need to get them in parentheses before I distribute. This is 1/3 times x plus 1/3 times negative 18. Positive times negative is negative, and 1/3 times 18 is 6. 1 third times 3y is y. And now I can switch these two sides of the equal sign around. Y equals 1 third x plus negative 6. All I did was change the order of the equation here. So this is the equation of the first equation. It's the same equation, just in a different form. It's in slope-intercept form, so now we can more easily graph the first equation. So let's come down to some graph paper here, and we're going to graph y equals 1 third plus negative 6. The y-intercept is always where we start, so we need to start at negative 6 on the y-axis. So here's where we're going to begin. And then our slope, which is the coefficient of x, is 1 third. That means I'm going to rise 1 and run 3. And when we solve by graphing, we use a straight edge to connect our points. And there is the graph of the first line. Let me get the arrows on here. And now we're ready to move on to the second line. The second line I will graph in purple. And first I need to put it in slope-intercept form. So I'm going to write the original equation, 2x minus 6y equals 12. And I'm going to change subtraction to addition by adding the opposite. And then I'm going to solve for y. So y is my variable. I'm going to get y by itself. I'm going to get rid of all terms without my variable in it by adding the opposite. These go to 0, leaving me with just negative 6y in the left-hand expression. And in the right-hand expression, it's going to be 12 plus negative 2x. I'm going to use the commutative property, though, to put the negative 2x first, because I know that in slope-intercept form, the x term should come first. Then I'm ready to multiply both expressions by the reciprocal of the coefficient, which is negative 1/6. In the left-hand expression, I'll have just y equals. In the right-hand expression, since I have terms, I need to put them in parentheses so I can distribute. Negative times negative is positive, and 2 times 1/6 is 1 third, and I still have a times x, plus positive times negative is negative. 12 times 1/6 is 2. So the same equation of the second one in slope-intercept form is y equals 1 third x minus 2. So I come down to my graph, start on the y-intercept, which is negative 2, and use the slope to find new points. Up 1 over 3, up 1 over 3, up 1 over 3, and then I use a straight edge to connect those points. Now, maybe you can see what's happening already. Here, what's the relationship between these two lines? These two lines are parallel, and parallel lines will never touch. Since the solution of a system of equations is represented by the points where the two graphs touch or intersect, if they never intersect, if the lines are parallel, there will never be any solutions. So this is what it means graphically for us to have an inconsistent system. Another way that we can tell that these two are parallel is once we put them in slope-intercept form, both of them had a slope of 1 third. And we know that lines with the same slope are parallel. So these two lines are parallel, therefore they will never touch. As a result, there will be no solutions to this system of equations. Now, remember how this looks when we solve using substitution. If a system is inconsistent when we solve using substitution, then once you simplify both sides of the equation, then you will get an equation with no variables that is not true. In a future video, we will discuss what happens when you get an equation where all the variables are eliminated, but the equation is true. For now, you need to know that if the equation is not true, the system is inconsistent. There are no solutions. So if you are working on this problem, when you get to this point, or if you were solving by graphing, and you get to this point and you realize they'll never touch, you would need to write, the system is inconsistent. And as a result, there are no solutions.